Review 1. So if you have a shaft, and I'm just going to draw a circular one, but you can have any geometry, and then it's subjected to a load, a force P. Okay, then the stress at, let's say that we want to compute the stress at some element like this. And then let's draw the axis. X, Y, and Z should point this way by right-hand rule. Okay, so in this case, we have sigma X, sigma Y, shear stress. So this is tau xy. So in this case, we would have clearly, there's only one stress, sigma x, and that is P divided by the cross-sectional area. The cross-sectional area is the area of the circle. And then sigma y equals tau xy is 0. Okay, so note that I wrote tau xy and not something else because that plane element is in the xy plane. Okay. The second thing is torque. So these are the easier ones. The harder ones are probably the moment and due to shear. So number 2, let's see what happens if you have a shaft. Subject. That's only axial loading, yeah. So we write that, yeah, it's a good point. First one is axial loading. Torsional loading. Okay, so let's draw the axis again. X, Y, Z. And this is now going to be a torque. Why does tau xy equals 0? Because there's no shear stress in the first problem. T only causes a normal stress. Shear stress tends to think of rubbing one paper against another one as you slide it. So there's no sliding, so to say, and that's why the shear stress is 0. The torque in this case actually leads to a shear stress, and the shear stress is, let's just draw the same element. Take an element on the surface and then blow it up. Okay, so the same thing here. You can draw the shear stresses like so. Tau xy is in this case not 0. In fact, it is, I'll write it down a bit, but the other stresses will be 0. Sigma y, sigma x. And I won't bother naming them, but they are sigma x and y. So sigma x equals sigma y equals 0, but the shear stress is not 0, and that happens to be non-zero because the torque leads to shear, and the shear stress in this case is T times C divided by J. Or if you like, I think I use C as a notation for radius. C is radius, K is the torque, J is the polar moment of inertia, which will be given. Okay, so if you draw the cross section, And then you plot the shear stress, and this is kind of important. What is the distribution of the shear stress? It turns out that it is 0 at the center, and then it goes to the maximum value at the edge. This tau max, which in this case is exactly this. Right? It is when you put the radius of C, then you have the maximum stress. And then if you want to find the stress anywhere else, you just divide it by the appropriate radius, and that will give you the shear stress at a different surface. But most times we are interested in the shear stress at the outer surface because that's the maximum stress. Okay, so torsional loading, let's do shear force and bending moment, and then we can get started with problems. Okay, stress, the third one is stress due to shear force. So for this, we think of something which is loaded in shear. So assume that there's a force P. And then we are trying to compute the shear stress on an element. Again, I'll draw the axis. X, Y, Z. Slightly bigger. So sigma x, sigma y, tau xy. Okay, so in this case, what happens is before I write the values for the shear stress, it's kind of important to see what happens to the cross section. So if there's a cross section, then you will see that the stress follows this profile, with the maximum occurring exactly at the middle, or what they call the neutral axis. And then it goes to 0 at the edges. So that is tau max. And tau is 0 here. And so what's that tau max is, so tau xy is, I just put tau here, but let me just put tau max, because this is the, so I did a, so the stress actually at the outer surface is clearly 0, right? Because think of this, this is the outer surface, it's 0. So when I draw this, I'm actually referring to the inner surface. So the better way to show this would be, think of, a better way to do this is probably this. I'm just going to cut it halfway. So this is the, so you can see it's like I drew a semicircle, but it's actually a full circle. But I'm just going to show the stress in the inner part. So the element is right in the middle, because the shear stress on the outer surface is going to be 0. It's going to be maximum on the inner surface or on the neutral axis. So what we do here is this tau max is 4/3 B divided by A. And this is for circle. If you have a square, this is for a square or rectangular cross section. This is something which will be given to you. So if you have a square like so, then it will be similar, but then the max would be different. Tau max is 3 by 2 v divided by a. This will be 3, 4 by 3, 4 divided by 3 v. And then the other stresses are 0. Sigma x is sigma y. Okay, one more and then we'll get started with problems. Okay, so so far this is the most important one, and this is where people make the most mistake. That this is the one due to the bending moment. So if you have the fourth one, stress is due to M. Or bending moment. Yes, in this case, let's consider a similar shaft. And then subject it to a moment. Okay, now, the way I'm going to draw the moment is, let's consider this is the x-axis, y-axis, z-axis, and it's kind of important how you have the moment. In this case, let's assume that the moment is in this fashion. So what is that? If you curl your fingers of your right hand along that the moment, then your thumb points in the direction of this arrow, the one which I'll show in, let's say, green. Okay, so this moment you see is along the z-axis because this is the z-axis. Okay, so when you have a moment in this fashion, what will happen is the stress in a cross section, which is along the x-axis, but in the zx plane will have a 0 stress. So that axis is something like this. Okay, so it's the horizontal, sort of the midway, but it's horizontal, and this is the what we call the neutral axis. The stress due to mz will be 0. So this stress is in the x direction, and if you redraw this figure, just the cross section, that's our neutral axis. Same thing. So what you'll see is that the stress is 0 here on the neutral axis. And then it increases linearly with the distance. Now, if you bend the beam in this, or this shaft in this fashion, then it will sag in sort of a U or a half U or whatever you like to call it, which means that the top part will be under compression and the bottom part is under tension. So compression, tension, right? You just visualize it instead of trying to think in terms of signs and values. I would just visualize it. Whichever side is elongated is the side which is under tension. So the bottom side is elongated, and so it's under tension. The top one is compressed, so it's in compression. So then we will see that the stress would be something like this, a little bit stretched. Okay, so this would be sigma min, because we said that the top part is under compression and the bottom part would be sigma max. And the value for sigma min and sigma max would be mz times y. Y is the distance from the neutral axis. So this is the neutral axis, which is along the mid of the beam. And so if you measure y upwards, and let's assume that the radius is, let's say c, then you have mc divided by I, where I is the inertia. And you could put a negative sign, just indicates the compressive stress. And sigma max would be mzc divided by I with a positive sign. Okay, so the key thing is that the stress is 0 in the middle. Sigma is 0. And then I say sigma min, it's just sigma x min. Okay, it's a stress in the x direction. Sigma x max. So then if you take any element which you want to consider on top, let's say, and draw the stresses, then what you expect is the stress would be max, or it's in this case min, my bad. It's on the top part, so it's min stress, sigma min, and that would be all the stresses on that. There's no shear stress because sigma mz cannot introduce the shear stress. If you take an element on the neutral axis and draw the stress element, all the stresses are 0. Sigma is 0, sigma x is 0, these taus are zeros. Because it's on the neutral axis, there's no sigma, sigma x is 0 as per this. And then if you go down, which is the last one, bottom, and then if you draw the 2D stress, this will be sigma max, and everything else will be 0, 0, 0. This is also 0, 0. All these are 0. Okay, so with that, you can actually do solve all the problems, which I'm going to talk about now. The thing which confuses people is, what if this moment was in this direction? Okay, that will be my. Okay, then you'll see that the neutral axis is not horizontal, but it's going to be vertical, not vertical, sorry. So it will sag this way. So it'll be vertical. The neutral axis would be just like this plane, the red plane I drew over here is horizontal. The neutral axis would be vertical, passing through the midpoint of the circle. So that's what confuses people. Just visualize it, and you'll understand how to draw where the neutral axis lies. So if there's mz, then the neutral axis along the zx plane in the middle. If it's my, the moment along y this way, then it's along the xy plane, passing through the midpoint or the center of the circle. Okay, so we'll do a few problems to make it clear. Okay, so this is a variant of, probably a variant of the problem you did for homework. The only change, how this problem changes with the one in the homework, is that I believe in the homework you had a force which was to the right, I think, and I drew it up. But changing the force changes the problem. And then if you want, you can solve this various ways. You can put this f up, you can put this f to the right, and you will have a different problem. So let's compute the stresses at A and B. Okay, so first thing I would do is take the element A, figure out which axis, along which plane it lies, write the stresses there, and then go and identify those stresses, and you're done. So let's do for point A. So I'll draw this element. Okay, I have to then draw the stresses. So we can see that this element is in the XZ plane. So we would have sigma X, should be this way, sigma Z, and then tau XZ, and tau XZ is the same as tau YZ. Sorry, tau XZ is the same as tau ZX because of complementary stress. Okay, so once we've done this, now the last step is to identify what the stresses are. Okay, so sigma x, sigma z, tau xc. Okay, so what I suggest is for a problem like this, you're better off identifying all the forces which are already there, F and P, and then identify all the torques which arise due to those forces. So in this case, we have two forces, F and P, and one moment is given to you. So let's try to identify what kind of moments are produced due to F and P. Okay, so P passes is normal to the cross section. It passes to the center. It's not going to lead to any moment, and so the moment due to P is 0. Now F will lead to a moment. The question is, what kind of moment will it lead to? F will lead to this beam probably bending this way, right? So it's going to cause a moment this fashion. So I can just draw that here. Okay, and then I think it's best if you show the axis. So if you curl your fingers of your right hand along that arrow I drew, then your thumb would be pointing in this direction along the dashed line, which means that the moment is along the z-axis, so mz. Okay, and then we know what mz is from the figure. We can see that it's F times the moment arm, which is 0.1. Okay, so here I'm really trying to focus on getting I'm not so much interested in the actual values, but I'm just trying to give you how to think about writing those sigma x, sigma z, and tau xz from the problem description. Okay, so now since we have identified all the forces and moments, let's try to write those stresses down. So P will lead to an axial stress along x. And since it's in the direction of positive x, I'm just going to put positive P divided by A, where A is clearly pi. The diameter is 15, so I just put pi d squared divided by 4. Okay, then the question is, what else? Will there be any other sigma, any other force or moment will contribute towards sigma x? Yes. Right, so because this movement causes, this is mz, it causes this beam to sag this way. The top portion of the beam would have a positive or a negative stress. What's the stress on the top, A, due to mz? Is it compressive or tensile? Compressive, right? Because if it's going to sag this way, then the top part is going to be compressed, or it's going to shorten. So it's going to be compressive. So the stress would be mzy, which would be d divided by 2 divided by I. And since it's compressive, it's going to be in this direction, sigma x due to mz. So it'll be negative. Yeah.
Okay, so when it's compressive, it's like bending kind of like this, right? And on top of my hands, there's like pointing down, right?
Arrows pointing down.
Like okay, so when you're saying it's compressive, right? Right? It's like bending this way, right?
Yes.
So
If
I'm doing it the opposite way, right? And I'm bending like this, compressive would be like in this region, right?
Compressive will be in the downward. So you're just saying, what if mz is negative mz? Then it will be, if the moment in the other direction, then the bottom part would be under compression.
Right. So so instead of bending like this, right? that's where the compressive, like, that's where the compressive region would be, right?
Is the palms of hand the top or the bottom part?
It's the bottom portion.
Yeah, then it will be right. That'll be compressive. Okay, so that's sigma x. Sigma z is the stress in z direction. So ask yourself, look at all the 3 or 4, I believe 4. We have mz. We have mz.
I have
We
a
have,
quick question.
yeah.
Can you explain why there's a negative?
Why isn't there what?
Why there's a negative?
Because this stress, let me draw it. Okay, this is a 2D view from the side view. Looking at it from there, there's P, which causes a stress in the direction I've shown. Since it bends, so bending, this is the top part, it's under compression. If something is bending here, then the stress has to be acting in this fashion. In other words, it has to be acting from right to left. So the sigma x due to m would be like this. So one of them is to the right, one of them is to the left, and that's why there's a negative sign. And I just stuck with the convention that positive is the one which is along the positive x. So this is positive, and this one is in the opposite direction, so negative.
So just to follow up, if our location of A is the opposite side, like at the bottom of the beam, so then we would have put a positive, right?
Can you repeat that? I couldn't hear you.
Oh, so I was saying if the location A was on the opposite side, like at the bottom of the our beam.
Yes, then if A was below,
Yeah.
then you're right. This should be a positive. This should be a positive.
And then if our moment is on the y-axis, how our beam bends?
Movement is along the y-axis.
Yeah. So in this case, our moment is in z-axis. So our beam bends are like a U shape, right? And then if it's on y-axis, how would it bend?
It will bend as a U, but then it will be in the it'll be a U again, but it will be in a different plane. So in the ZX plane, it will be like a U. So X Z plane, it's a U. Here it's a U in the X Y plane due to MZ. But if we had a movement in MY, then it will bend in the X Z plane. That's all. So then if yeah, go on.
So I was saying, so like, how would we know like how it's like bending? So like how to decide where's the compression and where's the tension?
You just look at the side, which is, I guess, convex, concave is confusing, but if you look at let's think of this as a U, a half U or a cut U, then whichever the inner side of the U is compression, the other side is tension. That's it. So you just have to figure out, okay, so the way it goes is, first I figure out direction of MZ, then I bend the beam in the direction of MZ. So it is originally straight. Because of MZ, it's going to be bent the way I've shown. And if it's going to bend as I shown, then the top part is going to be under compression. The bottom part is opposite, is going to be under tension. Similarly, if you have MY, which is not there in this problem, but let's assume it's there, then it will bend in a curve shape like a U, as I said, in the XZ plane. Remember, Z is here, X is here. So again, the top, not top part, but the part on the right, if you see it from this side, then the right side is going to be under compression because the top part of the U and the bottom part is under compression. So in other words, B would be here, right? So it will be under tension.
Then what about A?
A would be the neutral axis. It won't have any stress.
Oh yeah, got it.
But
Makes
the
sense.
neutral axis is this way.
Yeah, neutral axis makes sense. Thank you.
Yeah, so just don't want to confuse you with my, because there's another problem with this one actually has some interesting parts which will be with my. So I just want to keep that for later. So if you are confused with my, don't really get confused. There's another problem where I'll get to my.
Like, so inside of the U, right? It's compression.
Right.
And then outside, like the same way, right?
Yeah.
It's finding the other way. So inside the U is always a compression.
Yes, yes. So yeah, so that's a good trick. So one suggestion was, if you once you bend it down, the thing inside the U is always compression, and outside it's always tension. Okay, that's always true. So yeah, you can remember it this way if you want. And that's to an extent obvious, because if you have a straight beam, and if you bend it, then the top part is going to be decrease in length, the bottom part is going to increase in length. And that is, it's kind of maybe hard for you to see it here, but if you have like a thicker beam, not such a small one, but let's assume that this is the original beam. And now you apply a moment. Okay. Uh-huh. That will also work. Yeah, so this is exaggerated, but here you'll see that this length is shorter, this length is longer, and the length which does not change is the one in the middle. So the stress in the middle is 0. This is compression. This is tension. Okay, so where were we? So we've computed the stresses due to sigma x, and we have stresses. We need to compute due to sigma, now stresses in the z direction. So if you see F is not in the z direction, the torque is, well, it only leads to shear. So it's sigma z won't have a contribution due to T. P we saw is exclusively in the x direction. So sigma z is 0. And tau xz is going to be only due to torque. It's going to be T times the radius. So radius is d divided by 2 by j. I should put the values of j and I. J is twice of I, and that is pi d raised to 4 divided by 32. Yes. So, I mean, for an exam, this is like, if you can write this equation, and if you draw this part, that's like 90% of the points. What you do with the numerics is not very important, but what's important is that you are able to identify what the stresses are, and then you can write down the stress values. Once you have this, then you can do other things like, there could be a question on compute the factor of safety or one misses stress, but everything you do depends on getting this right. Right, so that's why this is kind of important. This is one of the things which makes it, I guess, this course a little bit hard, the combined loading. But you just break it down. For some people, it's much easier if they draw separate figures. Some people would just draw separate figures. So draw a figure for P, that is this diagram for P. Write the sigma x, sigma z, tau x z due to P, just like it drew in my review first part, right? Then draw the same figure for mz, same for T. And then once you have these 4 values for the 4 forces or moments, then you can just sum them up. So sum all the sigma x and you'll get the same answer. It's up to you. Okay, so let's do, well, I have to do part B. So let's see how to compute the stress at B. Okay, so first of all, note that B is along in the xy plane. Okay, so let me just copy that. figure again. Okay, now let's just start. I forgot, let me put the moment which were identified earlier. Z. Okay, so let's do the stresses at B. First of all, draw the stress element. Show the stresses. So in this case, at B, which is in the XY plane, we would have sigma X, sigma Y, and then tau XY. So that's the first step. Next, we will identify the stresses. So sigma X, sigma Y, tau XY. Okay, so again, we do the same exercise. First, let's figure out. So one of the two ways. One is you can ask yourself, what are the stresses in the sigma X direction, and then cycle through all those moments and forces and see what contributes. The other way to do it is to look at F and ask yourself, does F lead to sigma X, sigma Y, tau XY, and then put the value. So either way is fine. So let's just do the way we've been doing, which is let's try to identify sigma X by cycling through all the forces. So let's ask ourselves, which of those four things over here will contribute towards sigma X? Clearly P does. P divided by A, where A is the cross-section area. The torque only produces a shear stress, so it won't have a contribution. The F has a direction upwards, and it clearly doesn't contribute to stress in the X direction. And then we have MZ. Does MZ contribute towards the stress at B? What about MZ? Anybody? No, okay, no. So it's no because B is on the neutral axis. So the neutral axis for this MZ is this plane.
Professor, just to like picture, it's flat, right? On the, it's just lying on the beam, right? Flat.
Yeah, it's in the middle.
Makes sense.
Neutral axis for MZ. Okay, so that's it. It's just P divided by A. Okay, let's do sigma Y. Let's again cycle through all the forces and moments. Does F contributes towards sigma Y? So F, no, okay. So the answer is, well, it's no, but it's actually a very, there is a contribution due to F, but it's negligible. And let me just convince you why that's so. So F, you can see, is actually acting in the Y direction. So that force will cause a stress, but that's force, well, divided by the cross-sectional area will give you the stress. Now this area is, think of the way, so just like P gives a stress in the X direction due to this cross-section area, F will give a stress due to the fact that it is acting over the entirety of the cylinder, which is, if you think of this as A prime, which is the cross-section area, it will be F divided by A prime, right? Because it is basically a kind of an axial stress for B. However, since that cross-section area is pretty large, so compare this area with the area in red, this tends to 0. So, you don't have to calculate, you can just assume it to be 0. It's going to contribute almost nothing to the stress because of the large cross-section area. In other words, if the cross-section area is fairly large and the force is small, then you know that the stress is going to be 0 because the A is tending towards infinity relative to F. And so you don't have to write F divided by A, just write 0, and that's the right answer. Okay. And then finally, we have tau xy. So tau xy will be, again, let's cycle through this. PF don't contribute towards P doesn't contribute, MZ doesn't contribute. P doesn't contribute because it's an axial force. MZ doesn't contribute because it doesn't lead to shear stress. But F and T would contribute. In fact, for T, you would have, if you draw the cross section, the T is acting this way, as you can see. So at B, you would have, remember I drew this figure earlier, that the stress goes from 0 all the way to maximum. So the shear stress is maximum here. And that value is, let me write it in red, it's T times D divided by 2 divided by J. And then if you want, you can call it negative because it's pointing in the negative y direction at B. Now F will also lead to a shear stress, and that shear stress is because of shear load. F leads to a shear load. So if you draw a free body diagram of this, you'll see that the force at B is also F. And then the value for stress due to F would be, it's 4/3 V divided by A, where V is F. And so this stress is going to be in the direction of F, and it's positive because it's in the positive y direction. Okay, so that's yeah.
I have a question. So why there is a negative sign before TD by 2 over J?
Okay, so I stuck with the convention that if the stress is in the positive y direction, I'm going to put a positive sign and negative otherwise. If you look at the shear stress, the torque acts this way. I'm drawing the same torque, which is over here, right over here. So you can see that the torque will cause a shear stress profile, which will look like this. It'll be 0 here, it'll be maximum over there, and it'll be downwards because it's produced due to torque, which is acting counterclockwise. And because this tau max is in the negative y direction, I put a negative sign. And then F is upwards, it's in the positive y direction. It'll lead to a shear stress in the upward direction, so I put a positive there.
But isn't the torque is a positive x direction? That's how I was thinking.
Torque is
positive x direction if you curl your.
Oh wait. So on this element here, B, we would have, maybe I just switched the signs, hold on. But the relative sign should remain the same, but let's see if I got this right. So we have shear stress here would be this. So this element, yeah, so my bad. So the positive direction is actually downwards here by convention. So I would put a negative here and then positive here. Yeah, good catch. Yeah, so it should be positive, negative because of the way this is. We are okay. So this problem is taken from the book. I believe this was either posted as one I either solved a similar question in the class before, or it was part of a homework. Well, what I've done is I've changed the point which we need to find the stress from being top to that being on sort of the end on the axis, on the z-axis that I've shown, p bar, and you're told to find the stress. Okay, so there's a combined loading, there's a force, there are two forces, F and P. And so what I suggest doing first is figuring out all the forces and moments which act on this lever arm. And once you have that, then we can start thinking about stresses at P bar. Okay, but before we do that, we'll just follow the recipe we used last time, which is first the element P prime. That's our P prime. Identify along which plane it lies on. It's in the XY plane. If you draw a dot there, that's in the XY plane. And so we'll have sigma x, sigma y, and tau xy. So sigma x, assuming you're looking at it this way, sigma y, then tau xy. Okay. Now the next step is to figure out these forces, the stresses. Okay, so let's first, as I said, it's easier if you first figure out all the torques and moments acting on the lever arm, and once you have that, it's not very hard to figure out the stresses at P prime. So let's do that here. I'm going to redraw that figure, the stick figure, and let's draw the axis X, Z, Y. Okay, and let's draw the forces we know about. And here, in fact, let's just, you can just draw the forces at some different points. So here, it doesn't really matter. Okay, drew the forces. Those are the forces. There's no more forces. Now let's draw the moments. So let's do it one at a time. The first question is, what are the moments caused by P? And we can think that P will cause a moment this way. And so I'll draw that moment like so. And you can see that if you curl your fingers along this arrow, then your thumb will point in the upward direction. So that's going to be the positive y direction. So this is a movement in the y direction, and its value is going to be P times the moment arm. So the moment arm is going to be the distance from Z all the way to P. And you can see that it is 12 plus 2 plus 2, so 16. Now, does P cause any other torque or moment? I think that's the only moment. There's no torque due to P. Okay, so let's.
There's a torque path, right?
Yeah, so we get one by one. So let's compute the torques and moments due to PF. Okay. So we can see that one thing will happen is because of F, this lever arm can rotate, or F would lead to a torque. And if you curl your fingers along this green arrow, then your thumb, curl the fingers of your right hand. Okay, then your thumb will point in this direction as I've shown, and that would be a torque, and it will be in the X direction. So I'll redraw it here. Torque in the X direction. F will also cause a bending moment, and that bending moment would be in sort of this direction. So if you curl the fingers of your right hand along this arrow, then your thumb will point in this direction. So that will be a moment as you can see, it's a moment along the Z-axis. The Z-axis is right there. So it's going to be this fashion. Okay, to make this less confusing, here's my suggestion. Instead of drawing it this way, just draw it on the axis. MY. Yeah. We'll get to that later. Let's just identify the moments and torques. Next step would be to get the stresses. We'll get there. So I said this is an easier way. Just put the moment on the axis, and that way it's less confusing. So this is 16 times P. Let's compute TX and MZ. So MZ equals, so it's caused by F, and we need to figure out the moment arm from this point all the way to this, and it's the same moment arm as that due to P. It's going to be 16. So this will be F times 16. And then the last one is the torque along the x-axis. That would be F times the moment arm from this axis. So it will be times 15. So Px equals F times 15. Okay, so once we have identified all these moments and torques, now we can go to computing stresses.
So Z, that's the moment of Z. I thought there was only a moment about Y. Wait. There's a moment due to the force, right? The force F.
There's a moment due to force F, yes.
Yeah, and that's rotating around the axis.
Along the z-axis.
It's making the
Yes, that's right. That's the z-axis. So this is how this force will cause this thing to bend, or and so if you curl your fingers along this on the right hand, then your thumb will point in z direction. Okay, so now let's get to figuring out these values.
Professor, I have a question.
Yeah.
So can you just specifically tell, like, can you explain where the point P is like? Is it on the right, like on the side or on the top?
On the side.
On the side, got it. Thank you.
It's right here. It's going to get confusing. Let me use a different color for this.
what confuses me here is that there's a torque and a moment. Like that's just because I usually thought like the F force, right? You would just bring it to the location where C is, and that would be your bending moment around the axis, right? Is that where you're getting the F and Z?
Did I do a mistake? So P times, so the only torque due to P is going to be My, which I have there. And then F will lead to a torque.
Wait,
Yeah,
sorry.
that's right. Yeah.
Now, I get it.
Okay.
Sorry.
No problem. There's a lot of clutter here. I'm going to move this slightly down. We only need this now in order to figure out the stresses at P. You don't need the top figure. Okay, let's write, or maybe we do because it's a little hard to see. Yeah, we just need to vaguely remember where P prime is in order to write the stresses. So let's try to compute the stress in the x direction due to these loads. Now, what you can do is write sigma x equals and then try to go through each of those forces and moments and figure out if it will contribute towards sigma x or not. And that's probably the easiest way. So F, does it lead to sigma x? It's in the direction of y, so it cannot, right? F doesn't contribute. Px along the z direction, does it contribute to sigma x? It does not. So there's no contribution. What about Tx? Tx is something which causes a torque. It's going to cause a shear stress. It won't cause sigma x. Rule it out. We're left with two moments, My and Mz. Let's talk about My first. What do you think? My will cause a stress at P prime in the sigma x direction. So what will My do? Well, My in the top view of this, it'll cause it to bend this way, right? And if this is the shaft, then P is right here. So you can see that it is going to be stressed. So the My does contribute towards the stress. My times the radius divided by I. The radius is in this case, it's 3.5. Sorry, the diameter is 3.5, so 3/4 of an inch. Okay. Yeah, so I wouldn't go too much into exact value. We're just interested in figuring out sigma x, sigma y, and tau xy. What about mz, would mz cause a stress at P prime? So what mz does is, so this is the effect of, I should write this down. So it's the my. So mz will cause this to bend this fashion. So this is the z plane due to mz. Okay, where's P? P is right in the middle, right here. Okay, so P lies on the neutral axis. Or you can see it over here. If you bend it this way, then P is on the neutral axis. So my doesn't contribute, sorry, mz doesn't contribute towards the stress.
Professor, just a question.
Yeah.
So if our point lie on the top, right? So then mz would contribute and my would not contribute, right? If I'm understanding it correctly.
On the top, yes. On the top, mz will contribute and my will not contribute because it happens to be the neutral axis.
Got it. Makes sense. Thank you, Professor.
Yeah. Okay, so that's pretty much it. We've gone through all the 5 torque / moment / forces, and that's the only contribution. Let's see sigma y. Okay, sigma y is in the top direction. P is in a different direction, not along y. F is in the downward direction, but the contribution is almost 0 because F divided by cross-section area, the cross-section area is pretty large. So the contribution is going to be 0. And then the moments don't really give rise to sigma y. That's all 0. And then tau xy, which is a shear stress. Again, let's go through it one at a time. P, will it give to shear stress at P prime? Okay, so you're looking at the xy direction. The x is here, y is there. Since P is acting in the z direction, it won't really give a stress in the xy direction. So you can ignore that. F is acting in the vertically downward direction along y. Okay, so in this case, it will give rise to a stress. The only question is P in the middle or on the edges of that circular rod? It's basically in the middle. So if it's in the middle, it's going to give to a stress. So if you remember, the stress profile is like this, with a maximum occurring at the middle. This is for a circular cross section. There's 4/3 V divided by A, and it's 0 on the edges. But P prime is right there. So it will lead to a stress, which is given by 4 divided by 3. V in this case is F divided by the cross-section area, which is pi d squared divided by 4. Okay. And then, okay, so we've done with P, we're done with F. Now let's move on to Tx. Tx is a torque, and it does cause a shear stress along the circumference, right? So if you draw the cross section, you see that the stress due to tau x is shear. It's going to be maximum there. It's going to be 0 at the middle. This is prime. That's the max. And so the contribution due to that is going to be T times R divided by J. Okay, and since the way it acts downwards, and F also acts downwards, so both of them will have the same sign, positive sign. And then we can go through My and Mz, and you see that My and Mz only cause normal stresses. They don't cause shear stresses. So that's about it. Those are the 3 stresses. And something like this it'll give you most of the points. Of course, you need to then go back and fill in the dots and compute the values for tau xy if you're given numeric values. But this is worth most, like 90% of the points.
Professor, just a quick
Yeah.
question.
Yeah.
How did you get, I understand the F is acting downwards, that's why it's negative. Why the torque is negative?
Yeah, so if you look at this torque, you can see this arrow. This arrow suggests that this is going to rotate this way, or counterclockwise. Counterclockwise is on this figure is like so, and so the stress would be downwards.
Makes sense. Thank you.
Okay.
So I have a question. So our whole system rotate counterclockwise, right?
It will not rotate. Technically, it is held in place because there is some kind of a joint at P prime, but
okay.
Yeah, so that's why there's a stress. If it was free to rotate, there was a hinge joint, it was free to rotate, there will be no stress there because there it's free to rotate, there'll be some different stresses.
That makes sense. Thank you.
On what I've seen, how people make errors in problems. So here's a problem which is taken from the book. And the key thing I want to highlight here is, well, we'll talk about it. I think it's part, yeah, all these parts, you see that there's a conceptual thing about these questions and which people make a error. So compute the normal stress due to bending moment M. Well, there's no bending moment, but it will come once you do the bending moment diagram. Maximum shear stress to shear force P and maximum shear stress. Now, when you say maximum shear stress, this means that you need to compute it using the transformation of stresses. So in one plane, the stress would be sigma x sigma y tau xy, but there's a plane in which the shear stress is maximum, right? You need to find that. I believe I gave this question in the exam, one of the, right? Okay.
You said to find it in section 10. You said at a particular section.
I see. Okay, but let me just highlight the solution for this one. So there are parts to it which I think are kind of something which you know very well. So the first part would be compute reaction forces. Okay, and this is something which I would like you to practice. I don't want to solve it here. So the stress, the reaction force at O is 400 lbf, and it's acting downwards. The reaction force at A is 1200 lbf. It's acting upwards. So try to check your answers with this. This is important. Second is draw shear force and bending moment diagram. Again, I think this is something which you should be good at, and I don't want to spend my time doing this. So will just draw the shear force and bending moment diagram, and then we'll jump onto the actual questions. Okay, so this is how the beam is. There is, as I said, there's a force of 400 lbf downwards. There's an upward force of 1200 lbf. This distance is 8 feet, I think, and 8 feet on the other side. And then there's a distributed load. That's 100 lbf per inch. Okay, so this is all in inches. Inch. Okay, shear force diagram. It will look something like this. So 400 lbf is downwards, so there will be a 400 lbf force downwards. It'll all be 400 till you reach this point, which I think is called A. So here we'll have to add 1200 to minus 400, so that will be 800. It'll go all the way up. And then it'll keep going 800. Sorry, it will not. My bad. So if there is a distributed load, then that load will start producing sort of give a linear contribution to the shear force diagram. So we'll see that the shear force decreases, goes to 0. You can figure this out by taking a cross section and then finding the shear force, which will be 100 times x, and then it's basically, this is given by 800 minus 100 times x, where x will go from 0 to 8, right? So when it's 0, you have 800. When it is 8, you will have 0. So that's the shear force diagram, F. Let's draw the bending moment diagram. Okay, one way of doing that in this case is to take the area under the curve and then use that area to compute the shear bending moment diagram. So find the area here, which will be negative, find the area here, it will be positive, and then connect the dots. So it comes out to be 400 times 8, so it's 3,200. So it's negative, that's why I've shown it as negative. And then from A all the way to B, because the load is distributed, so you see the shear force is a line, and that will be a quadratic equation, to be a quadratic curve. Now it's, in order to figure out which way it will look, it will be this way or the other way, you'll have to probably write the equation and put a few dots and then connect it. But it happens to be the first one I've shown. This is how it is. It's sort of curves. This is a quadratic curve. Okay, so this is a bending moment diagram as a function of distance. Okay, so we've computed those. Now we are ready to solve for this part, second part. So now we are ready to solve for maximum normal stress, maximum shear stress, and so d2m, d2v, and so on. So if you look at this figure, okay, what's the maximum normal stress due to m? Okay, it's a straightforward problem because the maximum normal stress would be where m is maximum, because remember sigma is my divided by I. So we need I is constant for the beam. We need m to be max and y to be max. So m is max. So m is as a function of distance. So it's max over here. Part one. And where is y max? Y is the distance from the neutral axis. It will be on the top edge, right? Top or bottom? On the surface, right? So we have, for one, you say sigma equals m max y divided by I. Just put the values so we don't spend too much time. It's 3,200. Y would be, did I give the cross section? Oh, it's good, 1 by 2. So it'll be neutral axis. This is 1, this is 2. So this is y equals 1 divided by 1/12 bh cube. B is 1 here. H cube is the height, so 2 cube, and that comes out to be 4,800 psi. Okay, so we're done with part one. Part two, we're asked to compute the maximum shear stress due to V. All we do is look at the shear force diagram and find where it's maximum. So you can see it's maximum right here. This will be our part two. Okay, and so remember the formula is 4. This is a rectangular cross section, so it will be 3 divided by 2 V divided by A, right? And remember that the way it varies is it's maximum at the middle of the section, not at the edges. So part B, we have tau max is 3 divided by 2b over a, 3 by 2. V is given as, well, it's 800. That's the max. Cross-section area is, as you can see, it's 2 times 1. This comes out to be 600 psi. Okay, and then finally, so this is the part which is the more trickier one, where last time when I taught this, people struggled with this. So when you want to find the maximum shear stress, what you need to do is 3. So if you know sigma x, sigma y, oh thanks. So the way you find sigma max is that formula. The formula is basically giving you principal stresses, but that is the maximum sigma. You want to find the maximum shear stress. The maximum shear stress is given by this other formula, sigma x minus sigma y divided by 2. Okay, so this is what we are after. This is the formula we need for this. Okay, so what do we need to get tau max? We need sigma x, we need sigma y, and tau xy. Okay, and now when we do that computation, here we need to be very careful about, so we have these diagrams, and from these diagrams, we have to figure out where exactly the maximum shear stress will occur. Okay, you can see that a good candidate for the maximum shear stress is this point. Okay, in fact, I think that's the only point where you can have maximum shear stress, because so along the length x, the maximum shear stress will occur there because V is max, M is max, and you see that sigma is, it depends on M and tau depends on V or F. But then there's other thing, which is we know that it occurs here. That is the middle. But then the other question is, this is the cross section. Where will the maximum occur? Will it occur in the middle or on the edges? Okay. Remember that the maximum tau occurs in the middle, but the maximum sigma occurs on the outer edges, right? It's max here, this is max here. So what we need to do here is, and it's difficult to make that call unless you calculate it. So we'll compute the stress, the maximum shear stress on the outer surface. It doesn't really matter if you're upper or lower, it will be the same maximum shear stress. It doesn't matter. The maximum shear stress, yeah, will be, one of them will be positive, one will be negative, but doesn't really matter in this particular problem. Magnitude is important, yeah. And so we'll have to find the maximum. We need to compute the maximum shear stress here and the maximum shear stress here. So this is tau max for F, and this is sigma max for M. But the maximum for the combination would depend on the actual computation. So let's do that computation. So what I'll do here is, as I said, is the cross section. For part 1, we computed this value. It was sigma, and it was sigma x, and it was 4,800 psi. And we know for a fact that the shear stress at the outer edges or the edges is 0. So tau xy is sigma y is 0. And for the middle one, we have sigma x equals sigma y is 0 because that's the neutral axis. And then tau xy is 600 psi. Maybe bad choice. It can be a different color. It's confusing. So this is 2. We have sigma x equals sigma y 0 and tau xy equals 600 psi. So in order to solve for the third part, we use this formula which I wrote down earlier. and then evaluated both points. So let's call that say A and B. So at A, we have tau max equals 4,800 square. So it should be the whole square plus 0. Comes out to be 2,400. At B, we have tau max equals 0 square plus 600 square. Right, it comes out to be 600. So clearly the one which will keep the maximum stress is not B, but A. So this is our final answer. This is greater than the one below. So the max stress occurs at the point was A at the top or the bottom section, bottom edge of the beam. And the value is 2,400 psi.
Professor, I have a quick question.
Yeah.
So in this problem, it was asking for the shear max, right? Tau max,
Yeah.
basically. And then if we would have asked for the sigma max, would we have to do the same thing and then just use a different formula?
Yes, you'd have to use the other formula for principal stresses and do it, and then figure out the maximum. Yeah, absolutely right. You need to do the same calculations, similar calculations, but for principal stresses.
So the formula we will use, that's the one sigma A and sigma B one, right? So like
Yes.
in the
Yes.
equation sheet is, thank you.
Yes. Yeah.
Well, yeah, but this formula with, so you use sigma x and sigma y, and then you put these sigma x and sigma y
Right.
in order to find the principal stresses.
Yep.
And those principal stresses are sigma A and sigma B.
Yes, that's right. Okay, so here is kind of I think it's an interesting question in terms of driving some things about stress concentration. So here we are given capital D, small d, or we're given some dimensions, A, L, 0.5 L is where the stress concentration or the discontinuity is. And we're told to find the maximum normal stress and indicate its location. Okay, so these are simply supported. So think of this like a beam. So beam. Let's call this R1, R1, R2, and then it's of course loaded here. And since we are asked to find the maximum normal stress, we have to again go through the same process, which is compute the, draw the shear force diagram, draw the bending moment diagram. Once we have those two diagrams, then we can ask ourselves where will the maximum normal stress occur, and then use that for computing the corresponding normal stress. Okay, so first step, this problem is very similar to the previous problem in the sense it asks for the same thing, except that now we have a different geometry where we have stress concentration. So we use the same recipe. First, compute the reaction forces. This is at a distance of A, and A is, so it's A is 0.25 m, but L is 1, so it's 1/4, so it's 0.25, 0.75. And so I'll not spend too much time doing this. Just write down the answer. This is just doing the equilibrium of forces and moments, and you get R1 equals 75 newtons, R2 equals 25 newtons, such that they add up to P, which is 100 newtons. So once we do that, the second step is draw the shear force and bending moment diagram. Let's do that on a different page. So now we'll draw the second step, shear force bending moment diagram. R1 is 0.75, R2 is 25, and then P is 100, and this is 0.25, 0.75. Okay, let's get started with the shear force diagram. So 75 over here, so we need to go up 75. Okay, then it keeps going here. Then here we'll have 100 newtons going downwards. So 75 minus 100 will be minus 25. So we go down, minus 25, and keep going. When we reach the other edge, we go 25 up. So this is the shear force diagram. And this is 75. This is 25 minus. Okay, let's draw the bending moment diagram. Okay, so one way of doing the bending moment diagram is compute the area under the curve. So area under this curve is going to be 75 times 0.25. So a fourth of 75, 18.75. And in this, you will see that is also 18.75, just to 25 times 0.75. So we can easily draw the bending moment diagram. We just go 0 to 18.75 over here. And then minus 18, so it will go. So M X. Okay, just remind you about the geometry. So the geometry was something like this. At 0.5, we went this way. A little further. So this point was 0.25, but then this place where we have this discontinuity was at 0.5. Okay. Okay, so what we'll do is, there are two ways to solve this. Well, one is maximum normal stress. We could have case one where we have maximum stress due to M, and B would be just general principal stress. Okay, so I've not really specified here. Well, I've said maximum normal stress. So if you have maximum normal stress, you normally do principal stress and then solve it, which means that you need to first find sigma x, tau xy, and then solve for the principal stress. Okay, so I'm just going to not do that. Instead, I will assume that here we asked to solve due to M. Okay, so we'll deal with this, not because, I mean, this principal stress is just going to be more work. I just want to illustrate something about computing this value, and I think it will be more work to do B, so we'll do A, but I could definitely say maximum normal stress, in which case you would have to do it for principal stress. I'm just going to do it due to M. Okay? By M, I mean the bending moment. So what I need to do is, I only need to, in this case, look at the bending moment diagram to solve this. If I was doing it for case B, I'll have to look at the shear force and I will have to look at the shear force and the bending moment, find sigma x, and I think it'll be more work because I then have to do it at this point. I'll have to do it for this point, and I'll have to do it the stress concentration. It's actually maybe not too much work, but just to sort of give you the flavor of stress concentration, let me deal with the easier problem, or less computation rather than easier problem. It's just less computation. So I'm just going to compute max normal stress due to M. Okay. So we, in this case, we do not need to look at F. We only need to look at the bending moment diagram. Now, what we see here is the maximum normal force is over here. And if there was no stress concentration, that is the place where you have maximum stress and you're done. However, what happens here is there's a change in geometry here. So I suspect that the stress due to stress concentration would lead to a higher stress than that at this point. Okay, because you remember there's a KT you need to compute, and the KT when you which is normally greater than 1, if you multiply with the M, it will become greater than stress. Yeah, question.
Just by looking at the geometry, can't you just say like the maximum normal stress would be at that position?
Which
Stress concentration is that? Do you have to draw these bending moment diagrams and stuff? Because you're also given the force P. So you can just calculate it by directly just doing P over A.
P over A, no.
KT is equal to sigma max over sigma absolute, right, or something. It's,
No, you need to look through a table. You need to look through, there's a table, remember?
oh, yeah, it's fine, KT, sorry.
KT, you need to use capital D, small d, and R to compute KT.
Right.
And once you get KT, you need to then compute the stress at this point.
Right, but they give you that formula and it's force over area, right?
No, it's not force over area. There's no axial stress, no.
Oh.
This is not, this is a beam problem.
But they also, oh, you have to find the moment. Okay.
No, you have to find the moment. You cannot escape that. Now, if you guess,
But if you're giving the axial force, you don't have to find the moment.
there is no axial loading in this case.
But sometimes, like,
This problem has bending loads. See, you can see this diagram. Look at this diagram. This is a beam.
right.
So there's going to be a bending moment. There's no axial loads here. There's no force in the axial direction.
But you said that there's because I recall doing like, here, I'll just talk to you.
Okay. Okay, so we need to compute the moment here. And the moment there is, how can we get the moment? Well, we know this is a straight line. It starts at 18.75, it drops down to 0. And then we know this point, it is, so this is 0.25, this is 0.25, and this is 0.5. So it's a matter of figuring out, using the straight line formula and figuring out the moment M at this point. It actually comes out to be, so I will not do that. It's basically trigonometry here. So that comes out to be 12.5. Okay, so what we do is we will compute the stress. Let's call this point A and call this point B. So let's compute the stress at A and stress at B. So at A, this is standard textbook stuff where we find the stress at A as M at A, Y divided by I. The moment at A is 18.75. The Y is the distance from the neutral axis. And so we need this is the diameter. So we need D divided by 2. And I is going to be, I think I've been given all this. So D, small d. Okay. So capital D is 1.1. And then 1/12, the thickness is given. So it's 0.1 times the D cube, I think. 1.1 cube. And then you have to convert this. So you just write it down, convert it. 1.1 divided by 2 times 10 raised to -3. That's converting, is it negative? It's a -2 because we're converting centimeters to meters. Same thing here. -2. 1.1 times 10 raised to -2 cube. So this comes out to be 929 MPa. Okay, so that's the stress. Now let's compute the stress at B, which is this point. B. So at B, we have sigma B will be the KT, because there is a change in geometry, MB y divided by I. So let's compute KT first, and then we'll substitute that. See if we can do it. Yeah, I'll pull up the plot. This gives us KT.
Professor, why we are not multiplying by KFS by KT?
Say it again.
Why we are not multiplying by the KFS, not KT?
There is no fatigue loads. There's only static loads.
Oh, okay.
Okay, let's see if we can find it. Maybe it's this one. It's a question. Is this the one? This is not the one. Thought I had it here. Oh, that's the one. Okay, so what we have to do here is compute KT from this figure. So what we need here is R divided by D. So I'll write that down quickly. It's 1.1 divided by 1, which is 1.1. We need capital D divided by D. So that is, again, 1.1 divided by 1, which is, I'm doing something wrong. R is 0.1. My bad. Okay, so we have 0.1 R over D, and then we have capital D divided by D of 1.1, which is this. So it's this point. So 1.6, that's our KT. Okay, so we all set. Let's just compute this. Give me, okay, we still, okay, we are, let me go maybe a minute over time, and I'll be done. Okay, so at B, we said stress at B is KTM at B y divided by I. So KT is 1.6, moment was 12.5. Y in this case is small d divided by 2. So 1 divided by 2 times 10 raised to negative 2, convert to meters. 1/12 thickness, which should be converted to meters. So 1e negative 2, and then d cube. So that will be 1.0 times 10 raised to negative 2 cube. So putting all these values, you get sigma b equals 1200 MPa. Okay, so what we have is sigma A is sigma A was 929. MPa. Sigma B was 1200 MPa. So we see clearly that the maximum stress occurs at B. This is the max normal stress. So we were lucky that only 2 points in consideration, but if you have a geometry which changes, then you have to consider multiple points. So I'll stop